Earlier in the semester, we brought up this idea that reaction rates are path functions. And we used the example between path and state functions of something like climbing a mountain, where you might be down in a valley at the start and want to climb to the top. The overall change in altitude, the equivalent of perhaps a change in energy in a chemical reaction, was an example we used for a state function. But we brought up this idea that in climbing a mountain, you might take a variety of different paths. You might loop over this way. You might try to take some straight path that goes directly up to the top, but is a lot more difficult. There are options available. Now, if somebody asked you where you were along the path, you could provide them with information like your latitude, your longitude, your altitude, your whole position in this three-dimensional space. But I would suspect that if you wanted to tell someone where you were along a trail, you're much more likely to say, well, I'm on mile 2 of this 5-mile trail. Even when you're moving through a complicated space, you can still follow a path and describe your position along that path. We're going to do something very similar when we describe the pathways that reactants take to become products. We call that pathway the reaction coordinate. That reaction coordinate describes the path from reactants to products. Now, reaction coordinate is quite different from time. If we thought about what a given molecule was doing, it might be bouncing back and forth for a while, hanging out in reactants. It might go up this and down a little bit. It's bouncing around, and then eventually it makes it up to the top and comes down and becomes a product. This reaction coordinate is describing the path that reactants have to take to become a product. Because that is the path, that path tells us something about the rate. In particular, this position is the highest spot, the most energetic spot, the most unstable spot that our molecule or molecules have to follow in reaching the products. As a result, it's the toughest spot to get to. You can imagine this spot a little bit like a mountain pass. It's the high energy spot you have to go to, but there are still higher energy spots. The other spots just aren't relevant to the reaction. Now, if it's necessary to go up to this energy to make it over from reactants to products, then the difference in energy between our reactants and the top of that peak is called EA, the activation energy. The activation energy, we're going to see later on, is related to the rate of the reaction. Each possible pathway from reactants to products has its own peaks and its own possible reaction rates. So here I drew one possible pathway. Let's look at another. These pathways need to be determined through either experiment or theory. They cannot be determined from the chemical reaction equation. In this next example pathway that I drew, we have new, different possible activation energies. There's one activation energy along this pathway. We would then come down and stop here This I is a term we call an intermediate. So to write that terminology down, intermediates are structures that form along the way from reactants to products, but that are not going to stick around permanently. That's sometimes because they are unstable. For instance, in this case, the activation energy for this second step is quite small, and it's thus fairly easy for this intermediate to go down and become a product. Keep in mind that the height of this, the activation energy, is a measure of how difficult it is for a reactant to become a product. As a result, the larger the activation energy, the slower the reaction becomes. This is also why adding energy by heating up a reaction can cause a reaction to go more quickly. One of the features that we observe is that when there are multiple possible steps, so for instance, in this red pathway, there are 2 steps in the reaction. When there are multiple possible steps, only the slowest step determines the rate. We will refer to that as the RDS, the rate determining step. Just as a group of runners need to slow down to the pace of the slowest runner among them, a chemical reaction must slow down to the rate of the rate determining step. What we're going to look at next is an example of this approach where we can understand a bit better the relationship between rate determining steps and the reaction rate law.